Okay, in this video, we're going to be doing most of the first law of thermodynamics. It's going to be really important. The law itself is kind of simple, but the applications are kind of tricky. Before we can do that, we have to talk about what's called the zeroth law. I guess there was a first and second law of thermodynamics. They realized there was an assumption they were making that should have been the first law, or I'm sorry, that came before the first law, 0 comes before 1 and 2. And that assumption is that when temperatures are equal, no heat flows. Okay, now for the first law. The first law is all about changing the internal energy. Now remember that internal energy is U is the total KE of molecules in a gas. Okay? If I want to change the internal energy, okay, I want to have a delta U, I can. Okay, so to change kinetic energy, I have to make the molecules move faster, move slower. I have to change the temperature. So one way I can do it is to add or remove heat. Heat is Q, so I can add it or remove it, so plus or minus Q. The other way I can do it is to do work on the gas by compressing it. Okay, if I squeeze a gas, do work on it, and compress it, that means work is positive. Okay, and we have to know that if we say the words on or compressing, the work is positive because if I compress it, it gets hotter. That's increasing the internal energy. So work is going to be positive. It's going to make the internal energy go up. The other way is to allow work to be done by the gas by expanding. And in that case, work is going to be negative. When it expands, it cools. That can make delta U go down. We put it together, and we end up with the second law, which is that delta U, I'm sorry, the first law, is Q plus W. Okay? Now, the way to think of this, I think, is this. I think I have a certain level of internal energy. It's kind of like a bar graph of it. Now, I can add heat or remove heat. Okay? Or I can do work on the gas or by compressing it, or I can allow the gas to expand. If I add energy, if I add heat energy, if I add Q, the value of U is going to go up. If I remove Q, the value goes down. If I do work on the gas, I'm compressing it, making it hotter, the internal energy will go up. If I take work out of it, I allow it to expand, then the internal energy is going to go down. Now, this first example is going to be pretty straightforward, and to tell you the truth, if you can do this, there are problems like this on the AP exam. Now, I always have to identify what I'm looking for. That's the first most important thing. So what is the change in internal energy? Change is delta, and internal energy is U, so I'm looking for delta U. 800 joules of heat are added. Heat is Q, so this is Q. And when it says heat is added, that means it's going to be positive. And then 600 joules of work, so this is work. I got to figure out the sign for work. Now, if it's compressing, we know that work is positive, so this is going to be positive work. Now I look at my equation, delta U equals Q plus W, and I get delta U is plus 800 plus 600. Altogether, I get delta U is plus 1,400 joules. So I'm heating up the gas by adding heat, and I'm heating up the gas by compressing it. Those two together are making its internal energy rise by 1,400 joules. Now, the second example is a little bit trickier. Okay, I have, again, what am I looking for? What is the change in internal energy? I'm looking for delta U. I have 300 joules of heat are added. That's going to give me Q is plus 300. Okay. Now I know I'm probably going to be using this equation. Delta U is Q plus W. I find the Q, I have to find W. The problem is it doesn't give it to you directly. What does it give you? Well, it gives you a force of 400 newtons. And it gives you a distance, x, of 0.3 meters. And we should recognize that force and distance, work is Fx. So it's going to be 400 times 0.3. And that gives me 120 joules of work. Stop. Okay, it's important. Is work positive or negative? And what's going to tell me? Well, back here it says it's expanding. Expanding means work is negative. So I'm going to make this negative 120 joules. I'll make a note. It's negative because it's expanding. Okay, now I will plug that into my equation. So delta U is Q was 300 plus W was negative 120, and altogether I get delta U is plus 180 joules. So what's happening here? Altogether it's heating up. It's gaining 180 joules of internal energy. That's going to make it hotter. The 300 joules of heat that I'm adding would tend to make it hotter by 300 joules, but when I allow it to expand, it gets cooler, and it's losing 120 joules of energy that way, and altogether it's a net gain of 180 joules. Top of the next page, work and volume. Okay. Another way to find work is using this equation, P delta V, because if I change the volume, I'm either expanding or contracting, I'm going to be doing work. The other way to find it is the area below a PV line. And I'm going to do that in the next example after this one. First, we're going to use this equation. How much work is done in compressing a gas from 30 to 20 at the constant pressure of 1 atmosphere? So work is P delta V. The pressure, I need to have it in pascals, so I'm going to use this 1 times 10 to the 5th. And then the change in volume, if I go from 30 to 20, is 10. And that's going to give me a value of 1 times 10 to the 6th joules for the work. Wait a minute, we always have to say, is work going to be positive or negative? The way to tell is it says it's compressing right here. So that tells me work is positive, so it's going to be positive 1 times 10 to the 6th joules. Now, this example is long and involved, and it's going to seem kind of confusing, but we're going to practice these a lot, and I think by the end you're going to find you're pretty good at these. All right, so we have a graph of pressure versus temperature for a gas. It starts down here at point A, where the temperature is 300. Okay, it's taken to point B. Okay, I don't know the temperature up there. Maybe I can find it. All right, now, step 1 says how many moles of gas are there? All right, so what equation do we have that has number of moles? Number of moles is N, so we do PV equals nRT. I'll like to solve it. To get the N by itself, I would divide by RT. So N is PV over RT. So I look at point A because I know the temperature there. I can't do point B because I don't know its temperature. So at point A, the pressure is 1 times 10 to the 5th. So 1 times 10 to the 5th. The volume is 0.04. R is at constant 8.31. And T is 300. And if I plug this in the calculator, I get N is 1.6 moles. Okay. Step 2. What is the temperature at point B? I could use PV over T equals PV over T, but I think it's actually probably easier just to use Fervnerd again, because I know N now. So I'm trying to find temperature. I divide by N times R, so T is PV over NR. the pressure at B is 4 times 10 to the 5th. The volume is 0.06 divided by N is 1.6 and R is 8.31. When I do that, I get a temperature at B of 1800 Kelvin. So that's the temperature at point B. Part 3. 3 is going to be long and kind of involved. All right, we want to find the internal energy, not the change in internal energy, but the internal energy at point A. Remember, internal energy is U. It equals the total kinetic energy of all of the molecules. So first we have to find the kinetic energy of each molecule using this equation, 3 halves kBT. So it's 3 halves kB was 1.38 times 10 to the minus 23rd. And the temperature, we're trying to find it at A, and the temperature at A was 300. If I do that, I end up with a value of 6.21 times 10 to the minus 21. Remember, that's joules, but that's per molecule, for each molecule. Now, the number of molecules is equal to the number of moles times Avogadro's number. So I had 1.6 moles. I have to multiply that by 6.02 times 10 to the 23rd molecules per mole. Moles canceling at molecules. And I end up with a value of 9.632 times 10 to the 23rd molecules. Now when I put that together, for the total internal energy, I would get 6.21 times 10 to the minus 21st joules per molecule. Multiply it by how many molecules I have, 9.632 times 10 to the 23rd molecules. And the molecules cancel, I'm left with joules, and I get a value of roughly 6,000 joules of internal energy at A. Now, the next step, step 4, is asking me to find the internal energy of point B. And I could do this all over again, but I'm going to show you a shortcut. U is equal to 3 halves PV. Now, I teach it to you this long involved way we did in number 3 because it's important to know that the internal energy is related to the temperature. Okay, we had to use a 3 halves kBT. And it's the total kinetic energy of all of the molecules. So you understand what U is. Another reason is this equation, the U equals 3 halves PV, is not on the reference table. So you're going to have to know that it exists and memorize it when you get to the AP exam because you can't find it on the reference table. You can always do it this old way, even though it's longer. But for the shortcut, you're going to see how much easier it is. The total internal energy at B equals 3 halves. The pressure at B is, looking at my graph, 4 times 10 to the 5th. And the volume is 0.06. So the pressure is 4 times 10 to the 5th, and the volume is 0.06. When I multiply that out, I get 18,000. Nope, that's not right. I'm sorry. 36,000 joules is the internal energy at B. Now, step 5. What is the work done on the gas from A to B? Now I can use that work as P delta V equation, but I'm going to do it by finding the area underneath the line, because I said that's another way to do it. I want you to see that. I'm going to do it up on the graph itself so we can pick data from the graph. Okay? Now, if I look at my line, it's the area below the line. So there's my line, and it's the area down to the axis. Right? So I have to find the area of that shape. It's a trapezoid, and if you remember the area of the trapezoid formula, you can do that. But I split it up into a triangle, okay, plus a rectangle, right? So if I'm going to find the work, I'm going to find that area For the triangle, it's going to be base times height divided by 2. And then for the rectangle, it's just going to be base times height. Now the base of this, I go from 0.04 to 0.06. The base is 0.02. The height of the triangle is from here to here, so it's from 1 to 3. So it's 3 times 10 to the 5th divided by 2, because I'm doing a triangle, plus the base times height for the rectangle. The base is still the same. It's this 0.02. Then this time the height is here from 0 to 1, so it's going to be 1 times 10 to the 5th. And when I do that, I get that the work is equal to 5,000 joules. Now, before we go on, we got to say, whoa, stop, hold on a minute. I got to know if that work is positive or negative. To know that, we have to know, is it expanding or is it being compressed? Well, when I go from A to B, the volume is going from 0.04 to 0.06. So the volume is increasing, therefore the work is negative because it's expanding. Okay, so we're going to say negative 5,000. We'll say it's negative because it's expanding. All right, so then we'll go back down here, and we'll stay for step 5. See above, the work ended up being negative 5,000 joules. Okay, the last part is step 6. Is heat added to or removed? Again, it's important to say to yourself, what am I looking for? I'm looking for heat. What letter's heat? Heat is Q. I'm looking for Q. Now, we just found W, we found some U's. The only equation that I can use for Q here is delta U is Q plus W. Now, the W we just found is negative 5,000. We have to find the delta U. I'll do that over here. Delta U will equal the final minus the initial. So UB minus UA. UB was 36,000. UA was 6,000. So this is going to give me 30,000 for delta U. So now I can just plug that in here. 30,000 equals Q plus minus 5,000. And then Q, I have to add 5,000 to both sides, ends up being plus 35,000 joules. Since it's positive, it means heat was added. So 35,000 joules of heat were added to the gas. So that was a very long, involved problem, but I think you get pretty good at these as you go, and it shows just how much you can find from one of these graphs.